Negative 1 minus 3 times 2.
So negative 1 minus 3 times 2 is going to be minus 6, negative 7. Right? So now let's keep going. This is now 7 and 2. So the quotient is going to be 3 and the remainder is 1. And then tell me x and y. Negative what? Okay. So 1 by 1. So what is x? How do we find it?
Negative 1 minus 3.
3 times 4, right? Plus negative 13. And what about your y?
Negative 1 minus negative 1 minus 3.
You go 3 steps above. It's 2 steps. So what is that?
Negative 2.
2
Minus 3 times negative 7.
negative 7. Alright? So it's going to be 2 minus negative 21, which is 23. Right? So then, 2 divided by 1, the quotient is? 0. No, the quotient is 2, the remainder is 0. Right. So when you get the remainder as 0, it stops. Okay? So you stop and you don't need to compute the x and y, whatever the latest value of x. So you are actually finding the values of x and y in each iteration. Okay? So whatever the values of x and y at the time we get the remainder to be 0 are the final values. So what is that we can say? This negative 13, so we started with what? 53x plus 30y is 1. So if you want to verify, substitute the values, you should get 1. Okay? Now what we are really interested at, the multiplicative inverse, right? So this negative 13 is the multiplicative inverse of what in the class of what?
In the class of 23, right?
Negative 13 goes with 53, right? X. So it is a multiplicative inverse of 53. Whatever is multiplied with,
Okay.
right? So it's multiplicative inverse of 53 in class modulo 30. The other integer which is in 30. You see this is negative 13. So if you really want to work with only positive integers, right? So class modulo 30. So what is equivalent to negative 13 in the class modulo 30? How do you find that?
Add 1 to the 13.
Negative 13, right? In the class modulo 30. So I want to have an equivalent positive integer in the class modulo 30 for negative 13. Add what?
Add 1. Add to the next
Add
number.
30. So like
30.
if you add 30, you get what? 17, right? So 17 is equivalent to negative 13. Remember the table that I had in the first class? So class modulo 15, you see here for example, when 7 modulo 15, the remainder is 7. Then 22 mod 15, the remainder is 7. 37 mod 15, the remainder is 7. So all these things, the remainder is 7. And you can work with negative integers too. The only thing is, say for example you have negative 8. How will you find negative 8 modulo 15? Remember, division, if you work with negative integers, you have to repeatedly add until you get something between 0 and n minus 1. So you add a 15, right? Is it 7 or 15? 15. So 15 is going to be 7. So 7 mod 15. So this is between then if you work with, say for example, what else? 23. So if you want to find the equivalent integer which is positive between 0 to 14, right? Negative 23 mod 15 is 23 plus 15 is going to be what? Negative 8. And then negative 8 again plus 15 is going to be 7. So this is between 0 and 14. So that is equivalent. Okay? So like that, for negative 13, you want to find the equivalent integer in the class modulo 30. So what you have to do is negative 13 plus 30 gets you 70. And 17 is
plus
between
30.
0 to 29. So you stop there and say 17 is the equivalent. So you could say negative 13 is the multiplicative inverse, or you could say what? 17 is the multiplicative inverse of what? 53 mod in the class modulo 30. And you can verify by doing what? You multiply 17 and 53. Multiply 17 and 53 and do what?
A mod.
Do a mod 30. The remainder should be what?
17.
What you are doing here, multiplicative inverse, right? So when you multiply the two integers and take the mod of this, the remainder should be
1.
1. Right?
Okay,
Multiplicative inverse means the product should be 1. But the product in this case in the context of the class modulo the n. So in this case it's 30. Right? So that's how you can check whether you did right or wrong. Right? So now, are we really interested in this negative 13 or 17? 17 is the multiplicative inverse of 53 class modulo 30. Is that what you want to find there?
No.
You want to find what?
The 30.
30. Multiplicative inverse of 30 in the class modulo 53, right? So what we are really interested at? 23. Alright? But you should be able to do either way, whichever I ask, right? So I could ask you this, so you need to be able to do this. So in this case, you are interested at multiplicative inverse of 30, which is this 23. So 23 is the multiplicative inverse of 30 in class modulo 53. And if it comes out to be something greater than or equal to 53, you have to reduce it to something between 0 to 53. In this case, it is in between 0 to 53, right? So just stay with it. If it is say 83 or something, you have to do what? Like we did now here, we added, right? To bring it to be like between 0 to 30. If it is say 83, what will you do?
Subtract.
Subtract. Or divide, keep dividing until, just subtract. 83, right? Minus 53, which is 30, right? Alright, so now again you can verify by doing what? Multiply 23 by 30, the product, modulo 53, mod 53, you should be getting what? 1. Okay?
So you know if it's correct, it's gonna always be 1. If it's
Right.
correct, okay.
You did right. You can verify whether you did right or wrong. Right? Alright, so this I have another example here which I'll let you to practice. So we'll do one more thing and then we do RSA. Right? So you can practice? Okay? Alright. Let's do this RSA algorithm. So we did, again the first class, what I said. It's asymmetric, so we use two keys. Okay? Now, either key can be used for encryption and decryption. So the only thing is you can encrypt with one key and you can decrypt with the other key. You cannot use the same key for both encryption and decryption. Okay? So that's the underlying concept. So we are going to see how to generate the keys. Okay, the two keys. Again, you cannot say specifically encryption key, decryption key because you can use either one of them, right, for encryption or decryption. But like just for kind of Well, we'll see that. Yeah. So just to discuss, we'll say one key is used for encryption and the other key is used for decryption. So the way we are going to encrypt, so quickly we're going to see after this how we're going to find them, but how we do the encryption. So take up a plain text. We normally work with the integers. So the plain text could be the ASCII value of the character, for example, use characters that you want to encrypt. Okay, so we'll see a lot of examples. So take up the plain text, find p rise to e mod n. Right? So normally the encryption key is not a single quantity, it's given by the encryption key comma n, and the decryption key is also given by two things, which is d comma n. So we'll see how all these things are related. But encrypt, all we have to do is do a modular exponentiation, which we saw in the video last time, and we go over it again now. Alright? So this is your cipher text. Okay, so P, so for example, if this is something like 206 rise to 31 mod say 15. So you do this kind of math, and whatever you get out of it is your cipher text integer. Alright? And then to decrypt, what you do? You take the cipher text and do rise to the other decryption key, which is D mod n, and you get back your plain text. Alright? So how is this possible? Now substitute what is C. C is going to be P rise to E, right? So this C is P rise to E rise to D mod n. Okay? The C from this is P rise to E, right? And then you have this D, so that is again the exponent. So if you have something like this, I can write it as what? P rise to E times D mod n, right? So from math, if it is 2 to the power 3 rise to 4, it's nothing but 2 to the power 3 times 4. Okay? So, this is equivalent to what? I can just, again multiplication is commutative, right? So, I can write like this, P rise to D rise to E. So, this is why we say we can encrypt with one key and decrypt with the other, because this is still equal to what? The plain text, right? So, that's why with RSA we can use one key for encryption, another key for decryption, and vice versa. The only thing is we cannot use the same key for both. Right? So this is just to illustrate the commutative property, that you can encrypt with one key and decrypt with the other. It's not that one key has to be always used for encryption. You can always encrypt using either one of the two keys and just use the other key. Alright? Okay. Same thing again. Why? Because this could be written as 2 rise to 4 rise to 3. So you need not do always encryption with this key and decrypt with this key. You can always encrypt with this and decrypt with that. So that's what I like to do. Okay. Now there are a couple of properties I have listed. You don't need to really worry about this, but if you want, just it's good to know this. As I say, the complexity of RSA comes from the fact that, as you'll see, you will work with very large integers of the order of 100 digits, 200 digits, and so on. So you're trying to factorize a large integer of, say, 200 digits long and try to find its prime factors. Okay, so prime factors are, for example, the prime factors of 15 is 3 and 5. Okay, so 3 and 5 are prime. Right? So the prime factors of, say, any integer, right? So, for example, say 45 is going to be what? Can you find any prime factors for that? Huh?
45 and 1.
3 and 15, but 15 is not prime, right?
Mm-mm.
So you cannot find prime factors for every integer, right? So there are only certain integers for which you can find 2 prime factors. You're working with very large integers, so that's where it's very difficult to really factorize and find the 2 prime factors. We'll see as we see the details of how the key is generated, where the complexity comes from. Alright, so now, what will we do? As I said, you want to find these 2 keys. The encryption key, which is given by E, N, and the other key is D, N. Right? So to start with, I'll give you, so again from an exam point of view, you want to know what you're supposed to do. So I'll give you 2 things, P and Q. Okay? Both are prime integers. Okay? And this is what I'll give you and ask you to find the encryption key and decryption key. Alright, so given 2 prime integers, so for exam again we'll work with smaller integers, but in reality these 2 prime integers P and Q are kind of 100 digits long. Okay? And in a project you will work with such long digits by using this big integer class in Java. You already seen the project description. Okay? So we'll just work with smaller integers when you do for exams. So P and Q are 2 prime integers given to you. You want to find the encryption key and decryption key. The first step you have to do is find, so this is just a general sequence of steps, but we'll go through this example to make it easy. So the first step we have to find is to compute this n. Remember that encryption key is E, N and D, N, so you have to find this n first. And n is nothing but the product of the 2 prime integers. Okay? And this is 143, and this is where the complexity also comes. You see, one of these 2 keys will be a public key, right? Remember we talked about public key, private key. Public key is all known to everyone, right? So you see that if say E, N is the public key, the n part is known to everyone, right? So someone can try to factorize this n. If I factorize this n, I will get my P and Q. So once you get your P and Q, you can really try to find the private key, which is the other key, the decryption key, right? As we'll see. So the complexity comes from what? To factorize this n, which is in this case 143, and finding this 2 prime integers 11 and 13. Right? In this case it's easy because 143 can factorize, but if you have 200 digit long integer, you want to factorize it and to find the 2 prime integers, right, factors, that's where the complexity comes. Alright? So you want to really factorize this n, because when you display, like as I say here, in this case, in this example, it turns out both are the same, but like in the other example, they could be different. Okay? So you will announce the public, say this is your public key. You won't even say put the other key outside, it's the private key. So the public will know only 13, 391. So 391 they know it's the n. So they have to factorize this n, and n 391 if you factorize it is 17 and 23. Right? So these 2 are the prime integers. But this is easy to work with. But if you really have a larger integer, like 200 digits long, you cannot easily factorize. Okay? Clear? So given P and Q, the first step is to find your n. The second step is to find P minus 1 times Q minus 1. Right? So P minus 1 is 10, Q minus 1 is 12, so P minus 1 times Q minus 1 is 120. So
You lost me right there.
huh?
You lost me right there.
You lost?
I got lost. Yeah.
Okay, so I'll give you P and Q. Okay? You want to find the encryption key and decryption key. So given P and Q, the first step is to find n. So n is P times Q. Alright? And second step is to find P minus 1 times Q minus 1.
Okay, gotcha.
Okay? And P minus 1, Q minus 1 is 10 times 12 in this case, 11 is P and Q is 13, so 1 less than each of them. So the product is 120. So after we find this, now as we'll do in the project also, one of the two keys, encryption key, is actually your choice. You can really choose one of the two keys. Okay, so encryption key you can choose, and that will decide what is the encryption key, as we will see. Okay. Now again, for simplicity, we'll assume our encryption key has to be at least 10 or above, 10 or above. The only requirement is the encryption key, E, has to be relatively prime to P minus 1 times Q minus 1. Right? So if you write down the sequence of steps, as I have there, but I can write down one more time here. So the first step, given P and Q, find what? First find N is P times Q, and find P minus 1 times Q minus 1. So after we find this, the third step is choose the encryption key E such that E is relatively prime to what? P minus 1 times Q minus 1. No longer P times Q. We no longer want to Pn, Pq. We will work only with P minus 1 times Q minus 1. So this is where your GCD comes into picture. Why? Because, as I said, the encryption key is your choice, and we'll always in this course choose it to be 10 or above. Okay? So like in this case, your P minus 1, Q minus 1 is 120. So can 10 be your encryption key? No. Why? Because if you choose that to be 10 and you're working with 120, you're really looking at whether 10 and 120 are relatively prime. Or relatively prime, they're two even integers, so they cannot be relatively prime. Right? So just go there and go one more increment by 1. 11. Is 11 relatively prime to 120? Don't guess. Or verify. How will you verify?
Go through the process.
How do you define P minus 1 multiplied Q minus 1?
How we define it?
Yeah, I mean, how you can just define it, like you define that number?
Yeah, that's the kind of, is part of RSA. So you can consider this as a sequence of steps. We can prove the correctness of it, but you're not looking at it. Okay? Yeah, so this is the sequence of steps. It appears to you P minus 1, Q minus 1 suddenly comes from somewhere, right? Yeah.
Is it an error?
Huh? Iterative? No, it's not iterative. It's just given P and Q, find P minus 1, Q minus 1. It's a property. If you can prove this using number theory, but if you are taking number theory and cryptography course, you have more time to spend on the proof. We are not looking at it here. Okay, so just assume that you have to use P minus 1 or P minus 1. Okay? You have to know a lot more basics in number theory. You just covered the modular exponentiation part. So by the way, whatever we covered so far, the modular exponentiation falls under a topic called number theory. Okay, so this should have been actually covered in the math department. They have a separate course on number theory. And discrete structures they should cover a little bit for undergrads. Okay, but so we'll build on the top of it. Alright. So now, and algorithms, I'd like to add the BCD thing, as some of you might know, which was not covered before. So how will you find whether 11 is relatively prime to 120? The GCD, right? Find the GCD of 11 and 120. See if you get what?
1.
If you get 1, you have found the encryption key. If you don't get 1, you have to do what? Increment is 12. And 12 cannot be, right? Because you are working with 120, so it has to be 13. right? So you can skip one. I recommend working with smaller integers, but if you don't want to work with 11, you want to work with 30. In case 30 is greater than to 130, that's fine. You can go ahead. Okay, so 11 is not the only answer. But once you fix the encryption key, the decryption key will be dependent on that. Okay? Alright. Is this step clear? Okay? So the last step is to find the decryption key and how the decryption key is related. The decryption key D is the multiplicative. So as I say, this is choose for encryption, but here you're going to find the decryption key D, which is the multiplicative inverse of E in class modulo again P minus 1 times Q minus 1. Okay, so in this case, what we want to find? The multiplicative inverse of 11 in class modulo 120. So we want to find the multiplicative inverse of 11 in class modulo 120. Right? That's what we want to, that's how the decryption key is defined. And how will you do that? We just saw, right? This is just extended Euclid's algorithm. You want to find the multiplicative inverse of 11 modulo 120. So what will be your equation for mx plus ny? What will be that? Which is your m and n? 120, the larger one is always your m. Right? So you want to find the multiplicative inverse of 11 in the class modulo 120. So the larger one is always your m, the smaller one is your n. Right? So how will you write the equation then? 120x plus 11y is 1. So we want to find x and y, which is the Euclid's algorithm. So you write that chart. So now you can do in one chart itself. So this is 120, this is 11, this is your m and n, and this is your q, x, y, coordinates, this is your implementation step. Okay? So you hide it. So let's do this. So how will you proceed? Find the quotient, right? So 120, how will you find the quotient? 120 divided by